This video is about complex functions and their differentiation. The video is meant for the students of physics and engineering. In this video, this video being the first video, in this video we will introduce you to complex functions, their uniqueness, how they are different from real functions. We already know real functions. We know we have studied them in our previous classes, and we know from their study, we know that a function is basically a function fx is a rule that assigns a unique value fx to each point x in some set or in some interval on real axis. That is the essence of real functions. Let us first explain it a little bit what it means. Suppose you have a set of numbers, say we have 1, 2, 3, 4, 5 and so on. It's a set of numbers. Okay, then suppose we apply some rule and create a new set of numbers from them. For example, suppose we square them. When we square them, say when 1 is squared, it becomes 1. When 2 is squared, it becomes 4. When 3 is squared, it becomes 9. When 4 is squared, it becomes 16. So the rule that I have used for generation of these numbers is a square rule. I am squaring them. So if now you see this one has created this one, what we have done, we have this rule, this squaring rule, say I denote this, let me denote it by say x square. Call this is x, set of x, and this is fx, what you call fx. Now how do you create fx? How do you assign a value? Say these are values of fx. This rule, squaring rule, assigns a unique value. See, it assigns a unique value, say 1, to each point. To say 1, this one is assigned to this one. That means we have this one, and what square does? What does the square do? It creates another one from this. Similarly, you assign number 4 for this 2. You assign number 9 for 3. You assign number 16 for each. See, now a function fx is a rule. Here is the rule. Here in this example, x square is the rule. Square is the rule. Is a rule that assigns unique value fx, that assigns a unique value, this fx, to each point x. You can see, to this point this number, to this point this number, to this point this number, to each point x in some interval. Of course, the interval here is 1 to 4. The most important thing to realize is that we have a set here that has numbers. It's a set of numbers. Now, and here the set that we create, that is also a set of numbers. These are real numbers. This means that you know that real numbers are represented by a real line. This is a real line. 0, then 1, 2, 3, 4, and so on. -1, -2, -3, and so on. This is the world of real numbers, all confined to this line, none of them residing here or here or here or here or here or here or here, all confined to this. Now in a real function, if fx is a real function, then see, there is a, first of all, there is a set of this, you see, there is a set of possible values of x. See, this 1 2 3 4, this set of values of x, this set also belongs to this real line. Say from 1 to, suppose these are the only numbers in this set, the 1 to 4, say 1 2 3 4, 1 to 4, this is the set, this is the set. This set is called domain of the function, this set. And this set, the numbers generated by this rule are called the range of the function. Range, d, let d stand for domain and r stand for range. Now the both domain, the important thing is that both domain and range are confined to this line. This means that not only x is confined to this line, but also fx. 1 4 9 will be somewhere here, 16 will be somewhere here. That's why we say this is a function from R to R, where R is real, R stands for real numbers. Now you must not confuse it with graph of fx. In graph of fx, what you do, you plot x along this axis and you plot fx along this axis. That must not create a misconception that fx lives in some other world, in a world that is different from x. No, they are denizens of the same world, not of different worlds. This graph is meant only to examine variation, how fx varies with x. But other than that, one should always remember that fx also lies along real axis, not necessarily along x-axis, real axis. That is real line. Okay, now having said this, now there is one more thing now about these functions that we need in order to understand complex functions. One more thing, that is, suppose you have a function fx. Okay, say for example you have fx is equal to x square. Now good, if you change x, fx will change. Suppose I change x by a small amount delta x, fx will change. Okay, this change in this fx will change by x plus delta x, because new value of x is x plus delta x. This is the old value of fx, this is the new value of fx. If I subtract this old value from new value, what I get change in fx when x changed by delta x. This gives me changed fx when x changed by delta x. Now if I divide this change by delta x, then it becomes rate of change of fx with x. But this rate of change is average rate of change, or this rate of this also measures slope of fx, but average slope. Now to get to the actual slope, what we do, we take limit, we take this change delta x extremely small. When we take change in delta x extremely small, we obtain what we call derivative of this. That means actual rate of change of this, actual rate of change of fx derivative. We call that d, or we call that f dash x. We denote that by f dash x, where f dash x means dfx by dx. So this is what we have studied already. We know that this is the definition of a derivative. Now whether a function will have a derivative at a point or not, that depends upon whether this limit exists or not. If the limit does not exist, then the function will not have a derivative. If it exists, the function will have derivative. If a function has derivative, we say it is differentiable. If it does not have a derivative, we say it is not differentiable. That is so simple. Now, as an example, suppose we have fx is equal to mod x. Now let's try to find it as derivative at, of course, at say at x equal to 0, or let it be just let's without taking this x equal to 0, without imposing this condition x equal to 0, let us simply derive first an expression for its derivative. Then later on we will decide where we will find it is this derivative. Just a minute. Okay, now so what I need to do is, I have fx, I have this, I need fx plus delta x. So therefore fx plus delta x will be equal to mod x plus delta x. Okay, now if I substitute this here, there I get f dash x is equal to limit delta x tends to 0, mod, now see, you have mod x plus delta x minus fx, that is mod x divided by delta x. Okay, call it equation first. Now see, now this mod has a definition which depends upon whether its argument, I mean whether x is, so mod x, the value of mod x depends upon whether x is positive or negative. That is, we know that definition of mod x is this: fx is equal to mod x means mod x means x if x is greater than or equal to 0. If it is positive, then it is, there is no difference between mod x and x. If x is positive, that means plus 5, mod plus 5 is plus 5. There is not a bit of difference between the two. But if x is negative, say it is minus 5, this is not equal to minus 5. Minus 5 is not equal to, this is equal to plus 5. But how can you create plus 5 from minus 5? By see, here you do one thing, that is, you have minus 5, that is the number that was within these mod within these vertical lines. Now you have to multiply that by a minus. This will create a plus 5. This means that you have to change the sign of this. The original sign is minus, multiply it by another minus, it becomes plus. Now that means for x, this is true when we have to multiply this by minus. We have to multiply this by minus when you have a minus negative number here, but a negative number means a number less than 0. So we say that mod x is equal to minus x for all x less than 0. That means for negative numbers you have to multiply x by minus, only that you will get mod. Now interesting thing is that if we know which of the two values of fx should I use here, for example, which value should I use for mod x, that depends upon, this is now important, that depends upon from which direction are you approaching x. What does that mean? I'll show you what does that mean. Now here we had, say this was fx, and this was fx plus delta x. That means you are changing x from, x was being changed from, say, x to x plus delta x. Now in order to calculate actual rate of change at this point, what do you need? You need to change this x a little, but you have changed it too much. And if you now calculate rate of change of function at this point by taking the other value of the function here, because you need the other value, because in order to calculate the change, first you need to calculate the change. For change you will have to subtract fx from this. That will give you a change in fx. But the change that you are taking here is a lower change. It will not give you the actual rate of change at fx. You are interested in getting actual rate of change in fx. So what are you supposed to do? You are supposed to take delta x as small as possible. This means that instead of taking fx plus delta x here, bring it here. bring it closer, settle closer. Thereby you are decreasing delta x. You are decreasing delta x, change in x. Now bring it settle closer. Bring it settle closer. As delta x tends to 0, now delta x tends to 0. This means that x plus delta x is x plus delta fx plus delta x is approaching fx. Fx plus delta x, fx plus delta x is approaching fx. When x plus delta x approaches x. Now x plus delta x can approach x from two directions. You could have taken fx plus delta x not on this side of fx, you could have taken it on this side of fx. So there are two possibilities, one to the right of fx, other to the left of fx. You could have taken fx plus delta x here. Then in order to calculate actual rate of change, you would have to approach x from this direction. In order to decrease this delta x, take delta x as small as possible. You will have to approach from the left, approaching from the left. And in order to calculate in order to calculate rate of change by using this value, you will have to approach x from right, this left, this right. Now so there are two possible directions in which you can approach fx, in which you can approach x or fx. One is from left, another is from right. Now if the two limits, if we take now limit, if we now take limit when you are approaching approaching x from, say, right side, from this side. Suppose you are approaching x from this right side. The limit is then at that time called right hand limit. And if you approach the same x from this side, it is called left hand limit. Now the derivative will exist here. You will have a derivative here if these two limits are equal. They must be equal. Now suppose, let us try for this particular case. Since we have two definitions of fx, one applicable when you take x greater than or equal to 0, another when you take x less than 0. This means that when you approach x from right side, at that time you will have this x will be positive, because you are approaching it from right hand side. It will be positive provided fx is 0. That means you are approaching, yes, this is very important for us. That means we let us consider this x, the initial value of x, exactly at origin. Now is the time you are considering it at origin. Since you are approaching this x equal to 0 from from right, this means that the definition of fx that you will have to use is this definition, because x is greater than. And if you are approaching 0 from left side, then definition that you will have to use is minus x. Okay, now since we are approaching from, so let us first take the right hand limit. Let us take this right hand limit. What is wrong with it? This is our topic, and now so we have this is the topic. Okay, now we have left hand, right hand. First let us go to left hand limit. Let us do this thing. Let me calculate f dash x, that means derivative of fx when approaching limit delta x tends to 0 plus. It tends to 0 from right hand side. At that time you will have to use this definition of fx, this. So fx will be equal to x, but the first term in our formula is not fx, it is fx plus delta x. That means this fx plus delta x, fx plus delta x mod x plus delta x will be mod x plus delta x will be mod x plus delta x will be simply x plus delta x. Why it will be simply x plus delta x? Because the number being delta x being x being positive, so we will have x plus delta x for this fx. So x plus delta x, no difference. If this if you approach 0 from right hand side, then you will have to use mod x equal to x, mod x equal to x. That means mod x plus delta x, x plus delta x will be equal to x plus delta x, because both x and x plus delta x are positive, minus x for this for mod x divided by delta x, that will be limit delta x tends to 0 plus x plus delta x minus x divided by delta x, x cancels out, delta x by delta x, that is limit delta x tends to 0 plus delta x by delta x is 1. This is simply 1. So what we have got, right hand, from right hand the value of the limit comes out to be 1. Let us see from left hand, from left hand now from left hand, say okay, from left hand, f dash x is equal to limit delta x tends to 0 minus, that means you are approaching it from left hand, and now fx mod x plus delta x, that will be minus x plus delta x, because now x plus delta x is less than 0, and minus minus x. See, this is the minus of the formula, this minus, this is this minus, this minus, then mod x is itself minus x, so we have two minus there, so we have minus is divided by delta x, that is limit delta x tends to 0 minus, this will be minus x plus delta minus delta x plus x and minus x will go, you have delta x by x, that means limit delta x tend to 0 minus delta x by minus x, that is minus 1, this will be 1, minus 1. So what do you find? You find that the two limits do not agree, they are not same. We say that the function is not differentiable at x equal to 0. It is not differentiable, because if we approach it from one direction, we get the value of derivative plus 1. If we approach from the opposite direction, we get minus 1. Now, a function can be differentiable at a point, or it may not be differentiable at a point. This all depends upon whether you get this single value for right hand or left hand limits. Okay, now there may be other cases, there are other cases that can make a function non-differentiable, but let's not touch that right now. We will now go to complex functions. So what complex functions are? As the name suggests, complex functions are functions that have domain as complex numbers. Say for you have now again domain, this is domain, and in this domain you have now complex numbers. Say you have 1 plus iota, 2 minus 2 iota, something like this, 11 plus 3 iota, 3i. this is the domain, say for example, and if from this domain you create another set of numbers by some rule, by using some rule, say you can square them, you can cube them, you can for example multiply them with 2 and add them 3 and then divide them by 5. Any rule you can suggest, you can think of. From that, using that rule, you create another number, a unique number corresponding to this, a unique number corresponding to this, a unique number corresponding to this. Now in general, this range will be complex. You will create complex numbers from complex numbers. So this function, such a function is called a complex function. We usually denote it, instead of denoting it by, say, we use it to denote real functions by fx. Complex functions are usually denoted by w. In place of f we have w, and in place of x we have z. X is the real number, z is a complex number. And you know what complex number is, that you have in your mind. In general, a complex number can be written as x plus iy. Why x is its real part, y is its imaginary part. That much I hope that you know that thing. Now we then say that this wz, actually function is usually denoted by w, and the value that the function creates is usually denoted by wz. This denotes the value created by the rule. The rule itself is denoted by w, but often we will not make this distinction. But you should always keep this thing in mind, that the rule is one thing and what it creates is something else. It creates a value. That value is wz. Now, okay, this rule can be any rule. Say it can be square, for example. You can square this. Each number in the domain is denoted by z. We call that z. A complex number, since it is complex number, is denoted by z. Each z has two these parts, one x and this y. Don't consider this to be addition. You are not adding these two. You cannot. It is simply saying you that a complex number has two parts. One is x and another is y. This w is a join of the two. It joins them, not adds them. It cannot add. Okay, anyhow, this is the complex number. Now, when you feed such a complex number as domain, say you feed as domain this complex number, a domain element to this rule, it creates from this number another number. Now, suppose for example, as an example, let this be wz be equal to z square. That means the function is a square function. As we did in previous example, it is also a square function. Suppose now you create wz. You can see z is x plus iy whole square. Now that means x plus now x square plus I square y square plus 2ixy. Simple formula. Then x square minus y square, I square is minus y, plus 2ixy, or okay, no problem. See, this wz has two parts. One is a real part, this, and this is the imaginary part. We could have written it as this, like this, x square minus y square plus I 2xy. You can see now clearly that w2 has two parts. One is the real part, this it is real part, and this it is this imaginary part. Real part of w is usually denoted by u, and this imaginary part is denoted by v. We say w has two parts. One is real, that is u, imaginary this. Look, and this is very important, both u and v depend upon x and y. Both are functions of x and y. So we can write here uxy plus I vxy. Both are functions of x and y. Okay, now having said this, so we can now do one more thing, that is, see, you can now see parallelism between these two. You see the argument argument of the function, that is, it is domain. Domain member of the function has a real part and an imaginary part, and the function itself also has a real part and an imaginary part. That means a complex number, when subjected to a rule, creates another complex number. In general, it will create a complex number. Now, in special cases, you might have this imaginary number 0 or this number 0, but we are talking about general. In general, it will create a complex number. So in general, we will remember that if z is equal to x plus iy, then w will be equal to u plus iv. Remember, u and v both are functions of x and y. Now, I think it is clear. Okay. Now, the importance, there are certain unique things with complex functions. For example, one of the unique things that we are going to discuss now, and which is very important, that is Cauchy-Riemann equations. CR equations. Cauchy-Riemann equations. Cauchy-Riemann equations, you will yourself see what these are about. See, the point is this, that a complex plane is unlike a real number line. See, complex plane has two dimensions. One is, it has two, it is a plane, not a line. Like here is the real line. This is real line, or E, real line. It has a 0 somewhere here, and then positive numbers on this side, negative numbers on this side. Real line, in real line, numbers are confined to one dimension. And in a complex, on the other hand, a complex plane has x here and y here, say something like this. When you say this is a complex number and write it as x plus iy, it means that it has two parts, a horizontal a real part x and a vertical part y. This is very interesting. It is like a vector, and in fact, if we discuss its vector, this parallelism with vectors, that is a wonderful thing, but we don't have that in our syllabus. Needless to mention that complex numbers are among the few these mathematical structures which allow for division of factors. Division of factors possible in a complex plane. Now, again, we will not go into that, because that again is not in our syllabus. We will first confine ourselves to syllabus itself. Now, so a complex plane has two dimensions: real line, imaginary line. Okay, this imaginary line and this is the real line. It's not that graph. In graph you have this x and you have y here, but that y is just represent, that y shows us how this depends upon x. It shows the dependence on x. This is a graph. This is not like that. It is actually a world. You can think of this as a world in which live complex numbers everywhere. Each point of this plane represents a complex number, while as each point of this plane represents this real number. This cannot represent a complex number, because a graph of complex numbers is not possible as we do plot graphs between a real function. For example, say suppose you have fx is equal to x square. Now fx is equal to x square. You will easily plot it like this. Take x along this, take fx along this, and then plot. This you can yourself check it. You will get a parabola. Fx equal to x square, you will get a parabola. Okay. Now the same is not possible with a complex number, because if you have wz is equal to z square. Now see, this z requires two x's, x plus y. You see, z requires two x's, x plus y. This also requires this w requires two x's, u plus v. So this means that in total you need four x's to plot graph of a complex number. That, however, is not manageable, and it is that is at least impracticable now. So we don't go for this graph of these complex numbers like this. However, we have developed techniques or tricks by which we can extract information about how these vary. This varies with this. We can do that, and we don't have that. Even that is not in our syllabus, but we will touch that. We will touch a little bit of conformal mapping. We will touch that, and we have something like branch cuts in our syllabus. When we have an opportunity, we will learn more about this. But for the time being, this is one of the striking difference. Whereas you can plot an easily graph, you can plot a graph easily for real functions. The same cannot be done for complex functions. They require 4 axes. Now let us go back. Now there is one more thing, that is, this is a complex plane, and here suppose there in the plane is a number z0 is a number here, this z0. Okay, now suppose I want to see whether my function wz is differentiable at z is equal to z0, at z is equal to z0. What should I do? What should I do? I should take a nearby point, say z here, nearby point z here, for example, and then calculate the difference between the two. Let z be equal to zo plus delta z. This means the difference between them is delta z. And then calculate derivative of this. How? Derivative of this will be something like this: w dash z will be equal to, that will be equal to w dash z, that will be equal to, for example, z, this limit delta z tends to 0, and then in the numerator we will have the final value of this w, that is w z o plus delta z, value of the function at this point minus value of the function at this point minus w z o divided by the change in z from this point to this point. Now this is the corresponding definition of derivative. This derivative of a complex function at a point, say z0. Now this definition here demands something more than right and left hand limits. Had we been dealing with real functions, in real functions, suppose you have a number xo here, a number xo, and you want to find this derivative of fx at xo, what do? You take another point, nearby point, call that x is equal to xo plus delta x, and then you calculate their change. Okay, then divide that by delta x and let the limit tend to 0. But then there is a condition that this limit this limit should be same whether you approach this point from left to right side or from the left side. This must be the same. Otherwise, if you get two values of this function at one point, this becomes meaningless. Derivative of a point then does not have one unique value. It will lose that uniqueness. But that means there were two possibilities in real functions: approaching from left, approaching from right, approaching from right, approaching from left. In case of complex functions, you can approach this z0 from infinite directions. You can approach it from this, 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 you can approach it from this. You can think of many directions, infinite directions, and you can approach this. That means, this simply means the second point that you take for calculating this change, the second point that you can take that second point in this direction, you can take that z from in this direction, you can take z in this direction, you can take that second point in this direction, you can take there. In real numbers, in real functions, there were just two choices, and in complex numbers you have infinite choices. Now the important thing is that if you want that this differentiation of this complex function, derivative of this complex function at z(o) should exist, then all these must converge to the same value. My God. So that is the point. That is the point. The question now is, how can we know whether the derivative at this point exists or not? How can we know whether this function is differentiable at z(o) or not? There is an easy way, one easy way, which is necessary but not, of course, but not sufficient. In order to find the necessary condition, that means if a function has to be differentiable at a point, one thing, the first necessary thing that it has to follow is something that I'm going now to tell you what it is, that will be necessary. But then we will have to, after deriving the necessary condition, we will have to see what must be the sufficient condition. First, let us go to, without getting this confused, let us go to necessary condition. What is this necessary condition? See what I'm going to do. I will just select two directions, one along this horizontal axis, that parallel to real axis, the other along this parallel to this imaginary axis. This means that I will approach z(o). This is z(o) here. See, in real numbers, this point used to be on the real axis. In complex numbers, when we switch it to complex numbers, it cannot be on this. It can be, but that is a special case. In general, it will be somewhere here. Okay, number one. Number two, I will approach this z(o) from this side and this side. Only two directions. I will first approach only two directions. Now, if the two limits, this limit when I calculate limit approaching this from this side and the calculate limit approaching this person, if the two limits happen to be unequal, then the story is finished there. The story closes there. The chapter closes. We can declare that the function is not differentiable. But if the two happen to be equal, then then there is a chance that the function, but that is not, as you can see, that is not 100%. This we cannot certify, we cannot give it certificate that you are differentiable at z(o). We need to examine these as well. But at least if we examine first only two directions, this direction, and this direction, at least these the equality of these two is a necessary condition. That's a necessary thing. Then we will explore these things. But if the test fails here, what is the fun of exploring these things? That is what Cauchy and Riemann came out. They came up with this idea that these two must be equal. These two, if you take limit along this and limit along this, these must be equal. Now the question is, we have to now prove that these are equal. Okay. These are sorry. Will not prove that, but they cannot. It cannot be proved for every, because maybe a function may not be differentiable at this point. Now, how can we prove then these are equal? See, we have to derive the condition under which these will be equal here. So see, in general, I will write first. If I write, let me do one thing. That is, let me first change this. Say I have been taking this as say WZ as the notation for function. Sometimes students they feel there's this notation WZ is not a good notation. They want to continue with this F notation, and that is better. that in fact is better. Why did I use W? In order to stress that complex functions are unique in their own way. They're unique. But now I can relax that condition. Having seen this, at least two major differences between these real and complex functions, I can relax this condition and back to this f z will be, this function will be written by f z and then f dash, because we are so familiar with these notations. F dash means first order derivative of this, then f means second order derivative, and so on. Let me do one thing. Let me first define the derivative of z. Say this will be limit delta z tends to 0. Now final value of the function z plus zo plus delta z, final value of the function, that means this value. Final means this value of the function at this point, and initial value here minus initial value f zo divided by delta z. Okay, we know that in general we have f z is equal to, in general we can write f z is equal to u plus iv. This is both u, better it is to write u as this u xy, function of xy, plus iv xy. Now in terms of this expression, we can write, you see f z I have written as this u xy iv xy. Now if it is f zo, then that will correspond to, if z is equal to x plus iy. Okay, delta z will be equal to delta x plus I delta y. Okay, one more thing, zo will correspond to x o plus I y o. So keep this in your view. Now f z in general can be written as this, as you have seen that it has a real part and an imaginary part. Now f zo, value of the function at zo, that will be u x no xo yo plus I v xo yo. Okay, now similarly what will be f zo plus delta z, that will be u see what you have, see you have zo is xo plus iyo. Okay, but with zo you are adding delta z. This means that you are adding this. This means now when you are adding this to this, the real part will go with real part and imaginary part will go with imaginary part. So you will have here this xo plus delta x, this first xo plus delta x, that means zo plus delta z, xo plus delta x. This is for you. Plus now you have you also have this y part. Just a minute. Oh, sorry, I have this. I have to remove this. Yes, this is the way I can remove it. Now I have this is my this expression u now you have xo plus delta x. Okay, then you have y, you had here xy. Okay, xy, you have instead of x you have xo plus delta x, and instead of y you have yo plus delta x, delta y, sorry, yo plus delta y, you can check it, plus, because u is function of both x and y, this x, this y, and so is v function of x will now be xo plus delta x, y will now be yo plus delta y. Hope that you understand it. So when x had the value, when at zo x had the value xo, that is why I wrote here xo yo. Okay, XO for, because U also depends upon X and Y, XO YO, and V also depends upon X and Y, XO YO. At ZO plus delta Z, it will be, instead of XO must have changed now, XO by delta X, YO by delta Y. So is the case with this. Now substituting this in this equation first, if we call it, if we substitute it there, then we will get f dash z is equal to limit delta Z tends to 0, and then you have f ZU plus delta Z, that is this U XO plus delta X comma Y O plus delta Y, this is plus I V XO plus delta X YO plus delta Y. So I don't have space here, minus FZO, minus, let me write it, let me write it where, let me write it here, minus FZO, that is FZO, this U XO YO plus I will keep this in the brackets so that this plus is not altered, plus I have then IV XO YO, that. Now let us finish it. Now divide by, sorry, whole this is not divide. Now please don't treat it as division. Now divide by delta X, that is delta X, delta Z can be written as delta X plus I delta Y. See what I will do now. After writing this explicitly, I will do one thing. I will approach this ZO in this direction, parallel to real axis. When you approach ZO parallel to this, it means that you are not changing Y. That means you are not going up, you are not going down, you are only changing X along. You are approaching the point parallel to real axis. That means you are changing only X. So this will be my first case. That is, if I approach it from this, then f dash Z will be limit delta X tends to 0, because there is no change in Y, so delta Y, this will be 0. This delta Y be 0. Delta X tends to 0, and in that case, first let me rub this off, let it go. Now I have U XO delta X, because X is changing but Y is not changing, so delta Y is 0. You have YO. Let me try to write it in small size. IV XO plus delta X, that is okay. XO plus delta X, okay, but YO only. Then minus U XO YO, minus U XO YO. So YO, then minus into plus, that is minus IV XO YO, XO YO, XO IV XO YO. Hope that this doesn't create any confusion. XO YO, okay, divide by delta X. Right, now I will arrange this a little, rearrange this a little, writing delta X tends to 0. Then see what will I do. I will associate this with this and this together. So you have U X0, X0 or X0, whatever you like, the YO minus U X0 Y0, X0 Y0. This is X0 Y0 minus plus I V plus IV. I common, now V, you can write it here, V XO plus delta X, XO plus delta X, this X, XO plus delta X, comma YO minus, sorry, these two have to be enclosed in the same, okay, in the same, minus I has been taken common. You have minus X0 Y0, X0 Y0, whole divided by delta X. you can yourself see that this much is the change in u, due to a change in x. You are changing x and y is changing, u is changing. So I can break this into two parts. I will write limit delta x tends to 0. Then I will write u x naught plus delta x comma y naught minus u x naught y naught. Sorry, I am doing repeatedly I am doing mistakes. I am committing mistakes. I had to break this into two parts. I can do it settle, and I have this, say I have this u naught, okay, u naught x naught, sorry, and y naught here, y naught minus u x naught y naught divided by delta x plus I v, you can check yourself, v x naught plus delta x y naught minus v x naught y naught, okay, divided by delta x. So I have split this delta, not split, I have used it separately for this and separately for this. Now look at this. What is this? Change in u divided by change in x, change in v divided by change in x. This means that this the first part is a derivative of u, del u by del x, why partial derivative? Because u is here changing with x, not with y is held constant. So this is del u by del x plus I del v by del x. Here v is changing with x. So this is the value of derivative if we approach z(o) from this parallel to real axis. Call this equation 2. Now let us approach z(o) parallel to y-axis, parallel to imaginary axis. That means you will be approaching like this. In this case, y will be changing, but x will remain constant. So we have now f dash z is equal to, just a minute here, f dash z is equal to, you have simply to replace this delta x tends to 0 by delta y tends to 0. Delta x tends to 0 is to be replaced by delta y tends to 0, and then you have delta y tends to 0 u. Now x will not now change, y will change. That means x will remain xo, it will not change. Now y will change, that is yo plus delta y. Do you follow me? I hope you follow me. I am changing x, and here I am not changing x. X is the same, xo. Y is being changed, minus u x naught y naught, okay. Both are same here. So first let me eliminate this, delete this rather, then let me go to this, and I have now next is my this plus I, you have here iv, just a minute, iv. Now you can see yourself, iv x naught constant. Now y naught will change, y naught plus delta y, okay, minus this I v, if I take I common, then v x naught y naught, okay, divided by let put this I delta x, this I delta y, y. Now see, you can check here, you have delta x, delta z is equal to delta x plus I delta y. Now delta x now it is delta x, which is 0. So what is delta z due to this? So in place of delta z, I will write now I delta y here, dividing both sides. You know, this I will go with this I, and this I will transfer this I here, because you know that I can always multiply this by 1. Now 1 is equal to you can see minus I square. How? Because 1 is equal to minus I square, because minus I square is equal to minus 1. Minus into minus is plus. So imagine you have 1 here. Having 1 means you have minus I square here. Minus I square here. That is divided by this. I will go with 1I and you will be left with this. You have now you know that this much is the derivative of u with respect to y now. So you have minus I del u by del y, minus I del u by del y. I hope this is clear. Plus this is I goes, then this is del v by del y. In both cases differentiation now is with respect to y. So if you want that the function should be differentiable at z, then these two must be equal. Sorry, this was delta x. These two must be equal. 2 and 3 must yield the same value. This means, but that means what? That means del u by del x, del u by del x, del u by del x plus I del v by del x, del u by del x plus I v del v by del x. Not IV, it is I del v by del x, not IV, sorry. So it is deleted. After deleting this, let us go to this. It is I, what was it? I del v by del x. I del v by del x is equal to, that has to be equal to this minus I del u by del x, del y, sorry, u plus del v by del y. Okay, now if two complex numbers are equal, then the only way they can be equal is that their real parts must be equal and their imaginary parts must be equal, because you cannot equate an imaginary part with the real part. You cannot, same thing as you cannot equate crows with pigeons. Now you have this means this yields us two equations. Del u by del x must be equal to real part, and what is the real part here? Del v by see u. If you want to write u, please keep a little tail for it in order to differentiate it from v. Dv by del y. See, del u by del x, del v by del y. Okay. Now another equation is this must be equal to this. That means I del v by del x must be equal to minus I del u by del y. Now I goes, you are left with del v by del x is equal to del u by del y. Now this equation and this equation, these are called Cauchy-Riemann equations, CR equations. They are necessary conditions for a complex function to be differentiable. Necessary, I don't say sufficient, because you know I have explained that. Now these you will have to remember these. Now we will go for some practice questions and other things regarding CR equations. That will be in our next video. Thank you so much.